Today we start our discussion on second fundamental data type called character. Here is the outline of this lecture. Today we study a brief overview on character data type, the size of characters, range of characters, and we also talk about the difference between signed and unsigned characters. Let's have a brief overview. If you remember from the first lesson itself, I told you that how we can represent characters in computer. Recall this example of hello. And I also told you that how each character is represented with 8 bits of information. Computer is capable to understand only 0 and 1. Therefore, we need to represent characters in 0 and 1 form only. But we don't need to bother about it because internally it is all represented in bits form only. To encode characters, there are several encoding schemes available, but one of the most common encoding scheme is ASCII encoding scheme. This is an ASCII table that represents the ASCII encoding scheme. And here you can see there are some characters which are non-printable characters and some characters are printable characters. The non-printable one are the control characters and the printable ones are the characters you can print on the screen. ASCII uses 7 bits to encode characters. Therefore, we are available with 128 characters in total. If you can see here, this is from 0 to 127. That is, there are total 128 characters in ASCII table. But minimum to minimum, we have at least 1 byte. And as we know, 1 byte is equals to 8 bits. And ASCII requires just 7 bits to represent characters. Therefore, the most significant bit, that is 8th bit, is set to 0. Let's see how we define and declare a character variable. Here you can see I have declared a variable of character data type and assigned it a character. A variable could be of any name according to your choice. But if it is of character data type, it is capable of holding one character at a time. Note down these single quotes over here. Now this is important. Remember to put single quotes and not double quotes, otherwise you may get unexpected results. Character variable is able to hold only one character at a time. This is very important. If you want to provide a whole string to it, it won't be able to hold it because its size is equals to 1 byte and it won't be able to hold more than one character at a time. Now this is also not necessary to provide only characters to these variables. You can also assign integer values to them. For example, in this variable name, I have provided a value 65. Now this value acts like a character in itself when we are going to print it out. When we try to print the contents of this variable, we get a character instead of an integer. And that totally depends on the format specifier we are using. Here is the code. Here we can see I have provided a %C as a format specifier. If you put %D instead of %C, it will print the decimal value. But in this case, it will print a character. Let's see what would be the associated character value for this particular decimal value. As we know, the associated character for this decimal value 65 is A. That is why A is printed. If you see the ASCII table, you can see that A is associated with the decimal value 65. If you provide 65, it is similar to provide a character A. Now let's understand why this happens. Because after all, everything is in the form of bits only. Therefore, either you will write a character A or value 65, both are one and the same thing. Because their binary representations are same. The only difference between a character and an integer is that character is capable of holding only 1 byte of information. On the other hand, integer is capable of holding either 2 bytes or 4 bytes of information. Both can store integers. Both can print integers. But it is better to use them as what they are meant for. Let's see the size and range of character. Size of a character variable, you can say, or a character is 1 byte long. And range would be from 0 to 255 in case of unsigned character and minus 128 to plus 127 in case of signed character. This representation is coming from 2's complement representation. Unsigned range is because we have 8 bits of information available with us. Therefore, the maximum value that we would be able to represent would be 255. In the traditional ASCII character encoding, we have only 7 bits to encode the characters, and minimum to minimum we have to have 8 bits. Therefore, 8th bit is a total waste. There is one more encoding scheme called Extended ASCII Encoding Scheme to utilize the 8th bit, or you can say MSB bit. Therefore, the range is utilized properly in this encoding scheme. As you can see over here, that the range is from 0 to 255 instead of 0 to 127. Note, apart from the English characters, for the non-English speakers, we have to represent other language characters as well, like for Russian, German, Chinese, etc. For them, other schemes are available, but our concern is traditional ASCII character encoding scheme, which covers most of the special symbols as well as English characters and digits that we use in our day-to-day life, and most of the times that is sufficient. Therefore, we won't have to bother about the other schemes much. Let's move to the next topic, difference between signed and unsigned character. I told you the signed and unsigned range for character, but this is not an easy to digest fact that we have both signed and unsigned range of characters. Unsigned range is okay, but why signed range? In case of integers, signed range makes sense because in reality we are not only representing unsigned integers but signed integers as well. But what are negative values doing in characters? Are they buying some additional powers to us? Even though we won't require negative values at all, but as we know, internally everything is in the form of bits, so we can't resist ourselves to provide negative values to character variables. But the question is, what happens when we provide negative values to it? To understand this concept, let's consider the extended ASCII table once again. 0 to 127 is same for both signed and unsigned range. Difference comes in minus 128 to minus 1 in signed range and 128 to 255 in unsigned range. Let's write down the 2's complement representation of minus 128 in binary. There is one important point to note. Here we can see the place value is minus 2 raised to the power 7, and this is not usual case of when we are representing a positive value, right? This is minus 2 raised to the power 7. If we want to represent the negative 128, we have to set this bit to 1 and reset all the rest of the bits. Because this is minus 2 raised to the power 7, which is minus 128. Therefore, by setting this particular bit, we would be able to represent minus 128. This is the 2's complement representation. Always remember that the most significant bit's place value is always negative. In the case of positive numbers, this is quite easy because here the place value will be positive. If we set this bit to 1 and reset all the other bits, we would be able to represent plus 128. Let's try to represent minus 127. By setting this bit to 1 and this bit to 1, we would be able to represent minus 127. On the other hand, if I want to represent the value plus 129, this is also very easy to represent 2 raised to the power 7, which is equals to 128. And this is 2 raised to the power 0, which is equals to 1. So adding these two values together will give us the answer plus 129. As you can observe that these two values are equal. As in the previous case, these two values are equal. Minus 128 and plus 128 both have equal binary representations. Similarly, minus 127 and plus 129 have similar binary representations. If I would like to represent minus 126, this would be the binary representation, and for plus 130, this would be the binary representation. Both are equal. This is minus 128, and the rest of the numbers, if I add them together, this would be plus 127. Minus 128 plus 127 is equals to minus 1. Therefore, we need to set all values to 1. If we want to represent plus 255, then we have to set all these values to 1 similarly, but the only difference, as you can see, of this place value. That is why we are getting two different values, but with same binary representations. Okay, let's implement the code to understand. If we try to print minus 1 And if we try to print plus 255, both are one and the same thing. Let's implement the code. Let's see what character is printed for this particular value. This would be the character. If you see the extended ASCII table, then the associated character for this particular value would be this. Let's change the code a little bit. Minus 128 and plus 128 both are one and the same thing. Therefore, they must have to print the same character. Let's see whether they do or not. Yes, they are printing the same character. Therefore, it is verified that plus 128 and minus 128 both are same. Let's see what happens when we change this to plus 129 and execute it. This would be the character. And let's see whether minus 127 and 129 are same or not. Yes, they are same. Therefore, it is verified that all the things that we had studied up till now is correct. So the final conclusion is negative values won't buy you any additional power in case of character variables. Always remember that each negative value is equivalent to some positive value in extended ASCII character set. Because after all, everything is binary only. And one more thing. The idea of range exceeding condition for characters is similar to integers that we had studied in the previous lecture. Therefore, it is not worth mentioning each and every point once again. If you want, you can refer the previous lecture and relate the concepts accordingly. Let's have a summary of whatever we had studied up till now. Size of character is equals to 1 byte. Signed character range is from minus 128 to plus 127. Unsigned character range is from 0 to 255. Negative values won't buy you any additional powers. In traditional ASCII table, each character requires 7 bits. In extended ASCII table, each character utilizes all 8 bits. Okay friends, this is it for now. See you in the next lecture.